Dear students, in the last class, we solved the Schrodinger wave equation for a rigid rotator rotating in two dimensions or particle in a ring. Today, we will see how to solve the Schrodinger equation for a rigid rotator rotating in three dimensions or rotating in space. Rotation in space means that the axis of rotation is free to take any direction in space, and hence this model is also known as rigid rotator with free axis. Since it's rotating in space, this can also be considered equivalent to particle on a sphere. The wave function for a rotator in space depends on three variables r, theta and phi. But since we had assumed that the internuclear distance is fixed, r will not change, r is a constant. So the wave function xi will depend on only two variables, that is theta and phi. So we can write the wave function xi equals theta of theta into phi of phi. Here the particle is rotating in three dimensions depending on the two variables theta and phi. So we can solve the Schrodinger equation by separation of variables method. So let xi equals theta of theta into phi of phi, where theta is a function depends only on theta and capital Phi is the function which depends only on the angle phi. So let this be equation 1. The potential energy is 0 and there is no r term. So we can write the Schrodinger equation using the Hamiltonian, that is h cap xi equals E psi minus h square by 8 pi square I 1 by sin theta dou by dou theta of sin theta dou by dou theta plus 1 by sin square theta dou square by dou phi square into xi. So instead of xi, write theta into phi equals E xi, that is E theta phi. Now you have to divide throughout by, that is both LHS and RHS, divide by theta into phi. Minus h square by 8 pi square I. The first term becomes 1 by theta sin theta. Here you have to multiply with each term, and here sin theta dou by dou theta of theta into phi. There is no variable phi here in the first term, so phi will be a constant. So here it will become phi into dou by dou theta of sin theta dou theta by dou theta. And when we divide by theta into phi, that will become, phi and phi will get cancelled, so that will become 1 by theta sin theta d by d theta of sin theta d theta by d theta plus, similarly here also we have 1 by sin square theta dou square by dou phi square of theta into phi. Here phi is the variable, so theta will be a constant. So it will be theta into dou square phi by dou phi square. And when you divide by theta into phi, that will be 1 by phi sin square theta d square phi by d phi square equal to E. Let this be equation 2. Now you have to multiply equation 2 by minus 8 pi square I sin square theta by h square. We get the first term will be sin square theta by theta into sin theta d by d theta of sin theta d theta by d theta plus the second term becomes 1 by phi d square phi by d phi square equals minus 8 pi square I e sin square theta by h square. So after dividing by theta into phi, we have multiplied that equation by minus 8 pi square I sin square theta by h square. Now this on rearranging, here you can see that the first term depends on theta, and on the RHS also there is a theta term, sin square theta. Rearranging the like terms, we can write sin square theta by theta sin theta d by d theta of sin theta d theta by d theta plus 8 pi square I e sin square theta by h square equals minus 1 by phi d square phi by d phi square. Let this be equation 3. So when we look at equation 3, we can see that the LHS part depends only on theta, whereas RHS depends on phi. But these two are equal. That means both sides should be equal to a same constant, and let it be m square. Then we can write 1 by phi d square phi by d phi square plus m square equal to 0. That is d square phi by d phi square plus m square phi equals 0, where m square is a constant which is equal to 8 pi square ie by h square. So we can write, instead of m square, substitute 8 pi square ie by h square. So d square phi by d phi square plus 8 pi square ie by h square into phi equals 0. Let this be equation 4. Now, this equation is the phi equation. We have already solved the phi equation in the case of plane rotation, that is rotation in 2 dimensions. And we got the eigenfunction as xi equals 1 by root 2 pi e raised to im phi. It's the imaginary solution, and the real solution is 1 by root pi cos m phi and 1 by root pi sin m phi. And we also got the eigenvalue, that is em equals m square h square by 8 pi square I, where m equals 0 plus or minus 1 plus or minus 2, etc. Now taking equation 3, we got the solution for phi, and now the remaining part is to find out the solution for theta. So from equation 3 we can write sin square theta by theta sin theta d by d theta of sin theta d theta by d theta plus 8 pi square ie sin square theta by h square, these two terms, minus m square equals 0. Equation 5. Now divide throughout by sin square theta. Then we get 1 by theta sin theta d by d theta of sin theta d theta by d theta plus 8 pi square ie by h square minus m square by sin square theta equals 0. And let this be equation 6. Now we are going to give a substitution. Let 8 pi square ie by h square equals beta. So we can write 1 by theta sin theta d by d theta of sin theta d theta by d theta minus m square by sin square theta plus beta equals 0. Now if we multiply by theta, we get 1 by sin theta d by d theta of sin theta d theta by d theta plus beta minus m square by sin square theta into theta equals 0. Equation 7. This is called the rearranged theta equation. Now we have to solve this equation in order to find out the eigenfunction and eigenvalue. To solve this equation, let's define a new variable x such that x equals cos theta. Therefore, sin theta equals 1 minus x square raised to 1 by 2. You may be knowing that sin square theta plus cos square theta equals 1. So if cos theta is x, we can write sin square theta plus x square equals 1. So sin square theta equals 1 minus x square, or sin theta equals 1 minus x square raised to 1 by 2. So that's written here. Now d theta by d theta can be written as d theta by dx into dx by d theta. If x equals cos theta, then dx by d theta equals minus sin theta. Therefore, d theta by d theta can be written as dx by d theta is minus sin theta, so that is minus sin theta into d theta by dx. Or d by d theta equals minus sin theta d by dx. So now you can substitute the values of d by d theta and d theta by d theta in equation 7. We will get 1 by sin theta into minus sin theta d by dx of sin theta into minus sin theta d theta by dx plus beta minus m square by sin square theta into theta equals 0. So sin theta and sin theta will get cancelled off. Here we have sin theta into sin theta, that is sin square theta. Sin square theta is 1 minus x square. So expressing in terms of x, we can write d by dx of 1 minus x square d theta by dx plus beta minus m square by 1 minus x square into theta equals 0. Equation 8. This equation is known as the Legendre equation. Let theta equals 1 minus x square raised to m by 2 p of x, where p of x is a function of x only, and here the absolute value of m is taken. So if theta equals 1 minus x square raised to m by 2 into p of x, then first find out d theta by dx. So that will be equal to p of x into m by 2, 1 minus x square raised to m by 2 minus 1 into minus 2x plus 1 minus x square raised to m by 2 into p dash x. P dash x means dp of x by dx. And you will get like this. And then find out d by dx of 1 minus x square d theta by dx, which is in equation 8. So d by dx of this quantity 1 minus x square into this result, these two terms. And when you do the calculations, you will get the final terms like this: 1 minus x square raised to m by 2 plus 1 p double dash x or d square p of x by dx square plus 1 minus x square raised to m by 2 minus 2x into m plus 1 dp of x by dx plus p of x into 1 minus x square raised to m by 2 into minus m square plus beta equals 0. Now divide throughout by 1 minus x square raised to m by 2. And then you will get 1 minus x square d square p of x by dx square minus 2x into m plus 1 dp of x by dx plus beta minus m into m plus 1 the whole into p of x equals 0. Equation 9. And this is known as Legendre's differential equation. Equation 8 was the Legendre equation, and now we have find out Legendre's differential equation. Now we are going to simplify this equation by giving some substitutions. Let m plus 1 equals alpha and beta minus m into m plus 1 equals lambda. If we substitute for m plus 1 and beta minus m into m plus 1 in equation 9, we get 1 minus x square d square p of x by dx square minus 2 alpha x dpx by dx plus lambda into p of x equals 0. Equation 10. This type of equation can be solved by series expansion method. That is, we are assuming that p of x may be expressed as a power series in x. So if p equals a0 plus a1x plus a2x square plus a3x cube plus etc., dp by dx will be a1 plus 2a2x plus 3a3x square plus 4a4x cube plus etc. So d square p by dx square will be 2a2 plus 6a3x plus 12a4x square plus etc. And then we will substitute the value for p dp by dx and d square p by dx square in equation 10. So we will get 1 minus x square into, you have d square p by dx square. So write 2a2 plus 6a3x plus 12a4x square plus etc. minus 2 alpha x into dpx by dx. So that is a1 plus 2a2x plus 3a3x square plus etc. plus lambda into p of x. So lambda into a0 plus a1x plus a2x square plus etc. equals 0. Now multiply 1 minus x square with each term here. Similarly here also multiply 2 alpha x with each of these terms. And here multiply lambda with each of these terms. Okay. So you will get the equations like this. And now we have to equate the coefficients of each power of x to 0. So first consider the coefficient of x raised to 0. X raised to 0 means 1. That is, pick out the coefficients in which there is no x term. So first one is 2a2. There is no x here. And then another term that does not contain x is a0 lambda. So you can write 2a2 plus a0 lambda equals 0. Then next is x raised to 1. That is, you have to pick out the coefficients in which there is only the x term. The first it will be 6a3. And then you have 2a1 alpha. And then a1 lambda. So 6a3 can be written as 2 into 3 a3. 2 into 3 is 6. So 2 into 3 a3 minus 2 into 1 a1 alpha. 2 into 1 is 2. So 2 into 1 a1 alpha plus a1 lambda equals 0. Similarly, you have to take the coefficient of x square. So that will be, the first term is 12a4x square. So 12 can be written as 3 into 4 a4 plus the remaining terms are lambda minus 2 into 2 alpha minus 2 into 2 minus 1 into a2 equals 0. Now this can also be written as 2 plus 1 into 2 plus 2 a4 plus lambda minus 2 into 2 alpha minus 2 into 2 minus 1 into a2 equals 0. So similarly, if we write the coefficient for x raised to n, so that will be like n plus 1 into n plus 2 into a n plus 2 plus lambda minus 2n alpha minus n into n minus 1 into a n equals 0. So from this you can find out a n plus 2. So a n plus 2 will be equal to 2n alpha plus n into n minus 1 minus lambda into a n divided by n plus 1 into n plus 2. Now in this equation, if we substitute for alpha and lambda, alpha is m plus 1 and lambda is beta minus m into m plus 1. So if we substitute those values, we will get a n plus 2 equals 2n into m plus 1 plus n into n minus 1 minus beta minus m into m plus 1 into a n divided by n plus 1 into n plus 2. So we can write a n plus 2 equals n plus m into n plus m plus 1 minus beta into a n divided by n plus 1 into n plus 2. And this is known as the recursion formula for the coefficients in the power series of P. Now, in order to attain a satisfactory wave function, it is necessary that P should be a polynomial breaking off after a finite number of terms. So that means we need to put numerator equals 0. So if the numerator in this equation n plus m plus 1 minus beta into a n equals 0, then a n cannot be 0. So that means this quantity n plus m plus 1 minus beta equals 0. So we can write beta equals n plus n into n plus m plus 1. Here n and m are integers or 0. So that means n plus m will also be an integer or 0. And let n plus m equals L, where the value of L is 0, 1, 2, 3, etc. Then we can write beta is equal to L into L plus 1, where L equals n plus m. So we got beta equals L into L plus 1, where L can be an integer or 0. Now substituting for beta in the Legendre equation, we get d by dx of 1 minus x square d theta by dx plus L into L plus 1 minus m square by 1 minus x square into theta equals 0. Equation 11. The solution of this equation contains the factor called associated Legendre function, which is denoted as PLM of x. and that is defined as, that is the associated Legendre function PLM of x is defined as PLM of x equals 1 minus x square raised to m by 2 d raised to m by dx raised to m into PL of x, where PL of x is the Legendre polynomial of degree n, and its value is given by PL of x equals 1 by 2 raised to L into L factorial d raised to L by dx raised to L into x square minus 1 the whole raised to L. Here x equals cos theta and L is an integer including 0, and the value of m is 0 plus or minus 1 plus or minus 2 etc. So first we got Legendre function and then the associated Legendre function, which is defined as PLM of x equal to 1 minus x square raised to m by 2 d raised to m by dx raised to m PL of x, where PL of x is the Legendre polynomial. Its value is given by 1 by 2 raised to L L factorial d raised to L by dx raised to L into x square minus 1 the whole raised to L. So from this we can arrive at the solution of the Legendre equation, that is theta equals capital N into PLM of x, where n is the normalization constant and PLM of x is the associated Legendre function, that is the function p depends on L and m. The next step is to find out the value of the normalization constant. Now according to normalization condition, which depends on m and L, we can write integral 0 to pi theta into theta star d theta equals 1. We have expressed theta in terms of x. Since x equals cos theta, then the limits are from minus 1 to plus 1. So we can write integral minus 1 to plus 1 n PLM of x into n PL dash m of x into dx equals 1. N as a constant, so n into an n square can be taken out of the integral. So you can write n square into integral minus 1 to plus 1 p of x into p of x dx equals 1. Now the value of this integral minus 1 to plus 1 PLM of x into dx, value of this integral is n square into 2 by 2l plus 1 L plus m the whole factorial by L minus m the whole factorial, which is equal to 1. So from this we can find out the value of the normalization constant n equals 2l plus 1 by 2 L minus m the whole factorial by L plus m the whole factorial the whole raised to 1 by 2. Now if we substitute the value of n in the theta equation, we get theta equals 2l plus 1 by 2 L minus m the whole factorial by L plus m the whole factorial the whole raised to 1 by 2 into PLM of x, where x equal to cos theta. So this is the solution for the theta function. The complete wave function for the rigid rotator therefore can be written as xi Lm, xi the wave function depending on L and m equals theta into phi. So that is equal to the value for theta is 2l plus 1 by 2 L minus m the whole factorial by L plus m the whole factorial the whole raised to 1 by 2 PLM of cos theta into the solution for phi, that is 1 by root 2 pi e raised to im phi. So this represents the complete eigen function for a rigid rotator rotating in 3 dimensions. Now here we have considered only the imaginary wave function for phi. If you want to express in the real form, then that will be 1 by root pi cos m phi and 1 by root pi sin m phi. So we can say that the orientation of a rigid rotator is completely specified by the two angles theta and phi. These wave functions are customarily denoted by y Lm theta phi, and these are also called spherical harmonics. Now we also need the energy eigenvalue for a rigid rotator rotating in 3 dimensions. We had beta equals 8 pi square I e by h square, which was also equal to L into L plus 1. So from this, you can find out the value of E. So E equals h square by 8 pi square I L into L plus 1, where L equals 0, 1, 2, 3, etc. So this equation, that is E equals h square by 8 pi square I L into L plus 1, gives the allowed energy eigenvalues of a rigid rotator with free axis. That is the case of out of plane rotation or rotation in space.